we were here last time. We finished this slide. So we are at the bottom. So we complete this method. So this method, we can use this method to solve exact ODEs. Yeah. So what's the exact ODEs? Given the ODE in this differential form, and to be exact, it must satisfy this condition to be exact. Otherwise, it's not exact, but we still have a chance. Yeah. Next, later, near the end of this part, we will look at we can explore some more chance to solve this type of ODE, but this condition is not satisfied. Yeah. All right. So the method here, yeah. So this slide describes the whole method. Yeah. But this method, the last two steps, these two steps, we need to take partial derivatives with respect to different variable. Yeah. So here we need to do partial derivative with respect to y, with respect to x. Yeah. Because in that way, we can find explicit expressions for k prime y and L prime of x. After that, we can find k of y and L of x. Yeah. But this method, we want to simplify a little bit. Yeah. The next slide, I will give you an example. Demonstrate how to solve this type of ODE. But for this part, we want to simplify slightly. So we do not need to take, two partial derivatives. After we get these two forms, we can write out final solution immediately, based on some simple analysis. We can write out the final solution. Yeah. All right. Yeah. So the next slide, we will do that. Now let's move to example for exact ODEs. Right. Solve this ODE in differential form. Okay. Yeah. This one, it is exact, but we need to verify it first. So first, let's check the condition, exact condition. M function, capital M function, capital N function. Now let's take partial derivative. All right. Criterion, so this is a criteria, so we verify. All right. Partial M over partial Y, it's easy, so we can write it easily. Partial N over partial X. Partial N over partial X. Gone, first two terms gone. Take partial, same. So now we can move to a second step. All right. Second step, write u of xy in two different forms. Based on partial m over partial y, we can write our first form. Based on partial n over partial x, we can write our second form. All right. So based on this, okay, let me see. Yep. K of y. Yeah. So dx should be here, right? Yeah. Yeah. M or y. Okay. Yeah, let me see. Dx should be cosine, right? Yeah. Yeah. Okay. Yeah. So based on we have formula. So this m. Oh, here. All right. Yeah. Yeah. I used the wrong one. Yeah. All right. Yeah, it's correct because m is here. So you put it here. Okay. Yeah. Then sine. Yeah. Sine antiderivative. So sine switch to cosine switch to sine and no negative sign. Yeah. So sine. All right. So that's the first form. Second form, n. Yeah. Put here with respect to y. Yeah. Antiderivative for each term. First term, second term, third one, this function, and a little L function. Yeah. 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 All right. Yeah. So that's the two formulas we developed in the previous slide. Okay. Yeah. So we use these two. All right. Then the next step. Yeah. I want to do it in a simple way. Yeah. All right. Now, because u of x should take both forms here, both correct. These two forms, both correct. We have two different ways to write u function, both correct. So now let's compare. How can we make both formulas correct? So for the common term, well, no problem, right? Yeah. Common term, so we do not need to do anything. But for the different terms, then we need to do something. All right. First, look at two terms here. Y cubed plus y squared in the second form. Then you can think about it corresponds to k of y, right? Yeah. So k of y, this function should cover these two y terms that do not appear in the first form. Yeah. Explicitly. Yeah. So it should be inside k function. Yeah. All right. Then let's look at a little y. Little y, so little L function. Little L function, so other than, this is a common term. So we don't look at the common term. And k function, we skip the k function. Other than these two terms, no other k terms. No other k terms there. 0. Little L function, because we do little L function, when we compare these two forms, it corresponds to 0. Nothing. Nothing. Okay? Yeah. So based on this observation, compare two different forms. So we try to incorporate, the corresponding terms. Then we can write a final solution. Yeah. So let's write a final solution. Yeah, but this is the old method, all right? Yeah, this is the old method. Yeah, but here, yeah, we use the simple observation way, yeah, straightforward observation way. We can skip these two partial derivative way. Yeah. You can do it so you can try if you get the same answer. Yeah, but here, based on our observation. Yeah. All right, yeah. y cosine. Oh yeah. So here you can see. So here we have, here we apply, because we take partial derivative. We'll apply the old method. Here let's compare. Old method, we can find the K of function. All right, K of function. Then old method, we can find a little L function. Then we put them together. Here you can see we get this one. All right. Then, now I want to skip. I want to go from this step, jump to the final solution immediately. Immediately here, based on our analysis. Common term, sine function, common term. So we copy here. Y part, it should correspond to K of y, so we put here. Okay? L function corresponds to 0, so no contribution, but a constant. So constant, because at the end, so here, at the end, so here, constant. Constant, for this function, we write constant at the right-hand side. So left-hand side, we don't need to put a constant, okay? Because for the final solution, our final solution always take u of x comma y equals constant. That's the standard form of our final solution. Okay? So the constant should appear at the right hand side. Left hand side we should not include any constant. Okay? No need to include constant at the left hand side. So that's why we can easily go from this step based on observation, we can get to this final solution quickly. Okay? By observation, compare the terms. Y terms go to K of y function. X terms go to L of x function. In this way. Okay? All right. So that's the simple example. So if you do not feel comfortable on this simplified way, you just use the standard way. Okay? Taking partial derivatives. Then find K of y, L of x. If you feel comfortable, then you can do faster. All right. So that's this topic. Next topic. Now, next, we need to move to a new type of application problems. This topic, electric circuit topic. So before we look at those questions, we need to understand some background of the electric circuit in physics. All right. So look at this simple diagram. Okay. The components. Look at different components here. Okay. All right. In this diagram, so let's understand a typical electric circuit. A path for transmitting electric current. Electric current. All right. 3 types of components. All right. The first, electromotive force, EMF. Electromotive force. Power the electric circuit. A device that gives energy to the charged particles constituting the current, such as a battery or a generator. 2 types. Okay? The first type, battery type. Battery. Second, a generator. Yeah. All right. That's the first component. Second, devices that use current. That use current. Use current, right? Yeah. So, such as lamps, electric motors, or computers. Yeah. Yeah. Look at this part. Okay. Yeah. The connecting wires. All right. Yeah. Electric current. Yeah. Also, we need to understand electric current. A flow of charged particles, such as electrons or ions, moving through an electrical conductor. Yeah. All right. Just imagine. Yeah. Yeah. All right. Then, another concept, volt concept. Yeah. All right. The unit of electric potential, unit, yeah. So the volt here, there are two ways understanding. Yeah. All right. It's a unit, yeah. Unit of electric potential. Now, when you represent electric potential, you need to use some unit. That's the first way of understanding. Second way, another way. Electric potential difference, voltage, and electromotive force. Yeah. Yeah, because when you represent the difference of electric potential, yeah, because electric potential at these 2 points are different. Yeah. All right. Also, for electromotive force, you also have that difference part. Yeah. All right. Then, basic concepts in electric circuit. Yeah. So look at this diagram. RLC circuit. Three different types of components. R component, L component, C component. R, resistor component, L component, C component. Yeah. Okay? All right. So let's look at here. Yeah. Inductor. Yeah. Yeah. Inductor. Yeah. A passive two-terminal electrical component that stores energy in a magnetic field. Magnetic field when electric current flows through it. Yeah. So this component. This, see? You know, yeah. An inductor typically consists of an insulated wire wound into a coil. Yeah, coil part. Yeah, yeah. So this L corresponds to the inductor component. L, right? Yeah. All right. Yeah, because here obviously, although the component name, the device name, it's inductor, but we cannot use I to represent this component, right? Yeah. So resistor we use R, but inductor we cannot use I because we use I to represent electric current. Current we always use I. So for inductor, we should use a different symbol. Okay, all right. Yeah. Then the third type, yeah, capacitor. C, capacitor. Okay, all right. A capacitor is an electronic device that stores electrical energy in an electric field by accumulating electric charges on two closely spaced surfaces. Two closely spaced surfaces that are insulated from each other. Yeah, inside this cylindrical form, yeah, two closed surfaces. Yeah. closely spaced surfaces inside the cylindrical, device. Yeah. It is a passive electronic component with two terminals. Yeah. All right. Then a resistor. Yeah. A passive electrical component with the primary function to limit the flow of electric current. Yeah. Limit the flow. Yeah. Yeah. Control. Yeah. Otherwise, too easy, too fast, electric current. Yeah. So the resistor. Yeah. All right. Then we need to learn, review. Yeah. So I think you have learned these physical laws before. Now let's just review basic laws in electric circuit. Yeah, so here, 3 laws, okay? Yeah, here. Yeah, all right. Formulas, yeah, all right. So we use notations here. Ohm's law, the first one. Ohm's law states that the electric current through a conductor between 2 points. Yeah, 2 points here, 2 points, okay, 2 points is directly proportional to the voltage across the 2 points. Yeah. Voltage here, on the voltage between across the 2 points. Yeah. So there is a difference, right? Yeah. Electric potential difference between those 2 points. That's the voltage. Yeah. Directly proportional. Yeah. Directly proportional. Yeah. Yeah. All right. The formula V equals RI. Yeah. Voltage equals resistance, right? R. Yeah. Resistance. Current. Okay. Yeah. The current I. Yeah. Yeah. Voltage drop. Yeah. So here you can see here it uses the voltage drop. Yeah. Yeah. Look at that. So let's consider. We consider 2 points here. 1 point. These 2 points. Yeah. All right. At this point, you have voltage V1, right? Yeah. Then, so electric current goes through this resistor, reach this point, V2. And there is a voltage drop between these 2 points. Okay? So that part, that's the V part. Okay? V equals R, resistance. Yeah. So now using ohms as the unit. Yeah. Yeah. Resistor R, resistance R times the electric current. Yeah. All right. That's the first one. Inductance. Yeah. Now this one, regarding this inductance. Yeah. This law. Inductance is defined as the ratio of induced voltage to the rate of change of current causing it. Yeah. So that's so that's this law. Okay, this law. All right. Yeah. All right. Ratio. Yeah. So here, ratio of the induced voltage. Yeah, because here it's a voltage drop, right? Yeah. Yeah. So to see better, so voltage drop. So we use V, right? So V voltage drop, right? Yeah. So we have equalities. Okay. So the first one there. Yeah. Now we understand the second one. Second one, you can see defined. Actually, we define that inductance. So what's that inductance? This L is the inductance. Okay. So here we define this L. We define this L. Okay. All right. As the ratio. All right. So L. Yeah. So I mean, yeah. So I wrote this way. L as the ratio. Yeah. L equals V over this derivative. Okay. Rate of change of the current causing it. Yeah. So the current goes through. Yeah. Rate of change of the current causing this inductance, causing it. Okay. Yeah. And voltage drop. Yeah. We also have voltage drop. We put 2 points around this inductor. Yeah. So voltage drop between these 2 points. Yeah. So there. Yeah. So define that way, but we can write this formula. Yeah. All right. Capacitor formula. Okay. All right. Every isolated conductor exhibits capacitance called self-capacitance. Yeah. It is measured by the amount of electric charge that must be added to an isolated conductor to raise its electric potential by 1 volt. Yeah. So the way to define this, capacitance. Yeah. 1 volt. All right. So V equals Q over C. Yeah. Q Coulomb, unit, the unit of the Q, So the, amount of electric charge. Q is this amount of electric charge. The meaning of Q. Okay, yeah. C, capacitance. All right, yeah. Capacitance, yeah. All right, yeah. So that's the, some basic laws, yeah. We have a few more laws, yeah. So here are the basic laws, yeah. To get started, yeah. So later we need to use a few more laws, yeah. All right, yeah. Now, so let's work on some application problem. The first type, relatively simple one, RL circuit. You have resistor, you have inductor, you don't have capacitor, okay? So RL, only 2 types of devices, yeah. RL circuit. Yeah. Look at this diagram, okay? Yeah. E equals 48 volt. Yeah. All right. Then L 0.1 Henry. Yeah. The unit of this inductor, Henry. Yeah. H. Yeah. Then resistance equals 11 omega. Omega ohm. Yeah. Ohm. The unit. All right. Yeah. So in this simple electric circuit, model the RL circuit in this figure and solve the resulting ODE for the current I function. The current I is a function of t, time function of t. A, the unit, amperes, amperes, A, capital A, the unit. All right. Where t is time, assume that the circuit contains as an EMF, E of t. Yeah, it's a constant. So EMF could be a function of t, but in this example, 48 V, it's a constant, battery. Yeah. Yeah. If it's a generator, it could be a function. Yeah. All right. Which is constant. Yeah. A resistor of R equals 11 ohms. And an inductor of L equals 0.1 henries. Yeah. All right. Yeah. So very simple. The question. And the current is initially 0. Yeah. The current function, I of t equals 0 when t is 0, initially 0. Yeah. All right. Yeah. Then, we need to find I function, right? Solve the resulting ODE for this current function. Yeah. The goal, we need to find the explicit form of the I function. Yeah, here. Here we need to use a physical law called Kirchhoff's voltage law, KVL. Yeah. Kirchhoff's voltage law. Yeah. Yeah. Other than the basic laws, we need a few more physical laws. So what's that? Yeah, first, we need to write this law. Yeah. The voltage, the electromotive force, EMF, impressed on a closed loop, okay, is equal to the sum of the voltage drops. Voltage drops on the resistor and the voltage drop on this inductor. Yeah. Sum of these two terms. Yeah. All across all the other elements of the loop. Yeah. That's so simple, right? Yeah. That's the Kirchhoff's voltage law. Yeah. So we can set up an ODE using this Kirchhoff's voltage law. Left-hand side, constant, 48. Right-hand side, voltage drop, part 1. Voltage drop, part 2. Adding together, ODE. Yeah. And how to get a voltage drop from the previous slide, remember? So the previous slide, yeah, this place, the voltage drop, yeah, the formulas. Yeah. All right. Yeah. Voltage drop on this resistor, R times T. Okay? Yeah. R given, but the I is the function to be solved. I function. Yeah. All right. Then, voltage drop for the second one. L given, constant. L given, then the derivative of I function. Yeah. So let's, write this equation. Yeah. E equals L times I prime plus R times I. Simple ODE. Yeah. Very simple ODE. All right. Yeah. So let's, because we want to make the I prime stand out. Yeah. So we write in this way. Yeah. I prime divided by L. Yeah. All right. Then, yeah. So if we use Y, yeah, represent, yeah, yeah. So the variable, although you can use I, yeah, but here we can use, some the form we are familiar with. Y prime plus 110 Y equals 480. Yeah. Yeah. How to solve this equation? Yeah. Yeah. Actually, there are several ways. Yeah. There are several ways we can solve this equation. Yeah. But, for example, you can use separable ODE, right? Yeah, this can be written as the separable ODE. Then we can solve it easily, separable ODE. Yeah. Yeah. But here, in order to show you some special property or special way, special type of ODEs, so we go a different path. Yeah. We intentionally go a different path. Yeah. That way, that path actually harder than the separable way. Separable is the easiest way. Separable way is the easiest way. Yeah. So we will do it. So we do not need to use any new knowledge. New knowledge, our old way. Yeah. 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 But here there is some, because when we go a different path, we do more work. But this example, from this example, we can learn a new method. That's valuable. New method. Yeah. So that's the reason we go a different path. Yeah. Yeah. But if your goal is solving this equation, then the best way is the separable way. Best way, separable way. Easiest, fastest. Yeah. Yeah, but here, yeah, because our goal is learning, right? Yeah, here. Our main goal is learning the problem-solving methods. If that's our objective, then we go a different way. Yeah. And that way, there is some new problem we need to work on. Yeah. So let me show you that new problem. All right. First, we write it in the differential form. Yeah. So it looks like, because this simple way, we don't need to write differential form, right? Yeah. We don't need to write a differential form. But here, let's just do it. Okay? Yeah. Let's write the differential form and see what can we get. What can we get? Yeah. We want to get something interesting. Okay? Yeah. But here we want to explore, we want to develop some new method. That's more valuable, right? New method, yeah, more valuable. All right. So to write in the differential form, it's simple, yeah. Still also simple, yeah. Now, we use our previous method for exact ODEs, solving exact ODE. We have a method, right? Existing method solving exact ODEs. Let's try that. Because we have differential form, how to solve based on this differential form. Let's try the method we just developed for exact ODEs. First, we need to check for exactness. Is this ODE exact or not? We need to check the condition. Yeah. All right. Partial m over partial y, compare it with partial n over partial x. Yeah. It's very easy to find these two. Partial m over partial y. Yeah, this is m function. So 110. Partial n over partial x, yeah, that's 0, right? Yeah, that's 0. They are different. Not exact. Yeah. Now, we have a new situation. When we check the criteria for the exact ODE, we get, unequal. Yeah. These two numbers unequal. Yeah. So our next step, under this situation, what should we do? Yeah. Unequal. Yeah. Yeah. The direct thinking, yeah, because the condition is not satisfied, so we cannot apply the method solving exact ODEs. We cannot. Yeah. It doesn't work. Yeah. All right. But, so here, under this situation, our current method does not work. Yeah. Yeah. One way, we should develop a different method, right? Yeah, because it doesn't work. Yeah. We cannot do anything. So we should develop a different method. So that's one way, yeah, one possibility. Yeah. But then there is another way. There is another way. Yeah, people want to rescue the method, the method solving exact ODE. Yeah. Yeah. Do not throw away. So we want to find a way to bring it back. Yeah, that method. That's another idea. Yeah. Think about it. Actually, we take this approach before. Yeah. So in this class, we took this approach before. So what's that? Think about separable ODE. Yeah. Let's recall separable ODE. There is a condition, right? Yeah. First, we need to determine if it is separable. If it is not, what do we do? When we, based on our observation, if we see this ODE is not separable, do we still have a chance to make it separable? Yes, right? Yeah, we did that. Remember? Yeah. So one special case is right? This one we can make it separable, right? Yeah. Yeah. Another right? Yeah. Yeah. At the beginning, they are not separable. Okay? But when we do variable substitution, we can make it separable, right? Yeah? So we called, the method we use, we call extended separable ODEs. We can, so original ODE is not separable, but we can extend it. We do some special manipulations to make it separable. That's our experience. Yeah, we did before. Here, can we take the similar approach? Similar approach. Yeah. It's not exact. Can we do some special manipulations to make it exact? So we call it extended exact ODEs. Yeah. Yeah. The question is how to extend it. Yeah. It's non-trivial. Yeah. We need to do some work. Do some serious work to make it exact. Yeah. So that's the method we want to develop in our second half of this part. Yeah. First half, solving exact ODE. Second half, solving extended exact ODEs. Yeah. So based on this example, we want to go to the second half. Yeah. Yeah. All right. Yeah. Okay. All right. So this part, yeah. So we need to go to the extended, the method development, yeah, part. And after that, we can use that method, extended exact ODE, to solve this problem 9. Yeah, but I like to put it in the further explanation 1. Yeah, the details. Yeah, so I can save some time. Yeah, about 10 minutes. Yeah, class time, lecture time. Okay, all right. So next, I want to move to the extended exact ODEs, the method development. All right. Reduction to exact form by integrating factors. Yeah. Integrating factors. So we need to determine some special factor we call the integrating factor. Yeah. When we multiply this integrating factor on our original equation, we make it exact ODE. Yeah. That idea. See? That idea. Multiply a special factor. Yeah. All right. Consider the differential form. Here we use P function and the Q function. Okay? Different from our M function and N function. Yeah. Because M function and N function, we reserve it for the exact case. Yeah. When you use M or N, we assume this ODE should be exact. Yeah. If it's not exact, then we use a different symbol, P function and a Q function. Yeah. Okay. Yeah. All right. And we can assume partial P over partial Y is different from partial Q over partial X. Yeah. All right. Now, we need to find that factor, special factor. Yeah. So this is a simple, let's look at a simple example. Okay. So in this example, partial P over partial Y, -1, partial Q over partial +1, they're different. Yeah. Now, because this equality, we can multiply any function, both sides, right? Yeah. Yeah. Multiply, yeah. Any expression, both sides. Right hand side is 0, left side, we just multiply a redundant expression. It's redundant. Yeah. Some people may feel, why we need to multiply some redundant function? Redundant function, because it's not necessary. Yeah. But sometimes redundant work may result some meaningful property. Yeah. We can get some meaningful property by some redundant work. Yeah. Here, yeah. New idea. Yeah. Multiply both sides by 1 over x squared. Yeah. Some magic term. Yeah. Magic function here. How do you know? Yeah. Yeah. Later we will see there is a way we can find it. Yeah. How to find that magic function? Yeah. There is some form, some method we can use to find this function. Yeah. Here, just to show you the result. Yeah. Yeah. If we multiply this function both sides, yeah, we get a new differential form. You can see the new form and old form, they're equivalent, right? Yeah. Yeah. Or you can see they are almost equivalent, right? Yeah. Yeah. It may not be completely equivalent, yeah, because this function here, 1 over x squared, x is not allowed to be 0, right? Yeah? X can never be 0. When you take this form, in your solution, x can never be 0. But in the original ODE, x is allowed to be 0, right? Yeah, no restriction. That's the only difference. Yeah, so that's why I say not completely equivalent. Yeah, almost equivalent, slightly different. Restriction on the 0 point. That's the special point. You need to be very careful. Yeah. When you do this kind of manipulation, you need to know there is some special place. You need to pay attention. Yeah. After you find a solution, you need to double check that location, that place. Yeah. All right, so let's work on this new form. Partial p over partial y equals -1 over x squared. Then partial q over partial x, also the same function. Then it becomes exact. See? It becomes exact. There. So this simple example, you can see there is some interesting, if you can find this function, yeah, you can make the original non-exact ODE to be this new exact ODE. But they are almost equivalent. Yeah. It may not be 100% equivalent, but very close. Very, very close. Yeah. If we can solve the second ODE, then can we make small adjustment to get a solution of the first ODE? Right? Yeah. We can make adjustment. Small adjustment to get a solution of first ODE. Yeah. Okay? Yeah? All right. Yeah. So here you can see this idea is interesting. So this simple example gives us hope to find a special factor, integrating factor. Yeah. After we multiply that factor to this equation, both sides, that we can get an exact ODE. Then we solve it by exact ODE method. That's the idea. That's the extended ODE. Yeah. This method, just like similar to our extended separable, there is limit, right? Yeah. Not all non-separable ODE we can convert it. We can make it extended separable, right? No. Only the small portion of non-separable ODE we can make it extended separable ODE. Here the same thing. Not all non-exact ODEs we can make them extended exact. No. We can only later. Yeah. So I leave to the second half of the later. You will see we can only find the solutions for a small portion of non-exact ODEs. Very limited. Yeah, very limited. Okay. All right. So give you